Hi folks, this video is on the power law. We're going to start off by kicking it old school with some exponential laws. Here's one I hope you remember. X to the power a to the power b is equal to x to the power a times b. What this means is when we have an exponent raised to another exponent, we can just multiply those exponents together. So an example right here, x to the power 5 to the power 2 is the same as x to the power 5 times 2, or more simply, x to the power 10. Our bottom example here, 3 to the power 4 to the power x is the same as 3 to the power 4x. Now we call this the power law because we have like powers here, a power to a power, and we turn this power to a power into multiplication. We have something very similar over here in our log law where we have a power law. So here we have a power, and then we had a power turned to multiplication. And now this b kind of gets written out in front and is written as multiplication. That's exactly what our log law is. So when the argument of a logarithm is an exponential number, the exponent gets written out in front of the logarithm. So log base a of x to the power b becomes b log base a of x. So just to solidify this in your minds, let's run through a couple of examples. Our exponent is going to get written out in front. So this turns into x log base 2 of 8. Then we have the same thing here. Feel free to try this one before I get to it. Our exponent is going to get written out in front. So we get 4 times log base x of 2. So at some point in time, you might be asked to prove the power law, and this is our power law over here on the right. And I've just given you the starting point. So log base a of m is equal to y. So the first thing I want to do is I want to write this in exponential form. So the base logarithm moves to the other side. So m equals a to the power y. Then if we look over here at the power law, we have m to the power x. So what I'm going to do in my next line of work is I'm going to have this m, and I'm going to raise it to the power x, but what I do to the left-hand side must also happen to the right-hand side. So I'm really raising the left-hand side and the right-hand side to the power x. Now using our exponent law that we had before, we know that we can multiply these together to be a product. So m of x is equal to a to the power y times x, or I am kind of an alphabetical guy, so I'm going to call it xy, a to the power xy. And then I want to put this back into logarithmic form. So I'm going to move a over to be the base on the other side. So we have log base a of m to the power x is equal to x times y. And then by very definition at the start, we know that y is equal to log base a of m. So I'm just going to replace this y here. So log base a of m to the power x is equal to x, and we're going to replace it with our y. Log base a of m. And that's exactly what we have right here. And on to a few example problems. So our first one says simplify. We have a logarithm where the argument has an exponential number in there. So we're going to write that exponent out in front. So this simplifies to 3 log base 5 of x. Very similar style question. This one just says solve. So you'll notice that our first example had a variable. This one doesn't have a variable. But it's basically the same process. We're going to multiply this 5 out in front. So we have 5 log base 3 of 81. And then we want to evaluate this. We've evaluated things like this before just without the 5. So log base 3 of 81, we could say that is equal to x. Then put that in an exponential form. 81 equals 3 to the power x. Now because we have an exponent or exponential number over here on the right with a base of 3, we want to express 81 as something with a base of 3. So 3 to the power 4 is equal to 81. So I replace 81 with that. And then if our bases are the same, our exponents must be the same. So 4 is equal to x. So x was equal to log base 3 of 81. So I can replace this log base 3 of 81 with a 4. So we end up with 5 times 4, which of course is 20. Given log base 11 of a is equal to 2.575, solve log base 11 of a to the power 8. I'm going to start out by writing the question. And we're going to use our power law of logarithms to put the 8 out in front. So it's 8 times log base 11 of a. And then we know that log base 11 of a is equal to 2.575. So it's really 8 times 2.575. And then it's just a matter of doing this in your calculator. So we get 20.6. Write the following as a single logarithm. So now we're going to be combining all three of our log rules together. And this is the first time we're really using the power law kind of in reverse order. So we have a coefficient out in front of a logarithm, and we can move that up to be the exponent of the argument. Up to this point in time, if the 2 was here, we could move it down there, but we're just doing the opposite direction now. So this is like log of x squared minus log y. If you think back to previous videos, when we are subtracting a log, we can put its argument into the denominator. So this is actually log x squared over y. Now these brackets aren't necessary, but I'm just putting them there, hopefully so you can see clearly what the argument is. Feel free to pause the video and try these next ones on your own. So I see no coefficients to any logarithm, so there's no power law here, but we have a quotient law and a product law. So any logarithm that is positive ends up in the numerator, the argument ends up in the numerator, and any logarithm who's negative, its argument ends up in the denominator. So we have log base a of 5 times 8 over 4. Now this is written as a single logarithm, but it's not fully simplified. And I'm going to expect you to simplify these ones. So log base a, 5 times 8 is 40. 40 divided by 4 is just 10. Log base a of a minus 2 log base a of b plus 1/2 log base a of c. So we have all three log rules applying right here. We have the coefficient in front of the logarithm, actually two different ones, so both of these numbers are going to become exponents. And then we have something that's going to a denominator and something that's going to a numerator. So I'm just going to do this kind of one step at a time. So we're going to put the 2 as an exponent. Then we're going to put the 1/2 as an exponent as well. And now I'm going to combine these first two because there's something else I can do with this third piece. So log base a, and this one's positive, so a is in the numerator, and then we actually get b squared in the denominator. And I'm going to keep this other one separate just for a moment, and it's going to be log base a. And when you have an exponent that's a fraction, that really means we're going to get a radical in there somewhere. So when the denominator of the exponent is a 2, that means we have a square root. So this is really the square root of c. Now, this logarithm is being added, so this root c gets to go in the numerator of our argument. So log base a of a root c over b squared. This whole thing is the argument. In our last example, this 3 is the only coefficient, so I'll write that as an exponent right off the hop. So that's going to be b cubed minus log 3 of c. And then I'm going to combine everything. So log base 3, a is positive, so it goes numerator. B cubed is positive, so it goes numerator. And c is negative, so it goes denominator. Fully expand each of the following. So this question is the exact opposite of the previous question. Before we had several different things, we want to combine it into one. Now we're going to have one thing, we want to combine it into several. So anything in the numerator is going to be positive, anything in the denominator is going to be negative. So this gives us log base a of a plus log base a of root c minus log base a of b squared. Now if we want the full expansion, this exponent has to be written out in front. So log base a of a plus log base a, and this root c is the same as c to the power 1/2, just like we had in our previous example. And then minus 2 log a of b. We still have this exponent that needs to get written out in front, so this is going to be our last line of this question. So that is the full expansion of this expression. Let's try the next one. So anything that was in the numerator is positive. So this is positive, and then we have a 2. Plus, we have an x, so it's log base 3 of x. And then y is in the numerator as well, so plus log base 3 of y. And nothing else in the numerator, but we do have the z in the denominator, so it's going to be minus log base 3 and root z. You might remember when we had this root c, it ended up turning to c to the power 1/2. So I want to do the same thing with this z. I'm going to call this z to the power 1/2. Then to fully expand, this 1/2 gets written out in front. Just like so. So given log base a of 2 is equal to 0.3562 and log base a of 3 is equal to 0.5646 and log base a of 5 is 0.8271, find log base a of the square root of 10 over 3. So this is probably the most difficult question we're doing in this video. And the reason is that we kind of have to expand what's going on here into things that are either log base a of 2, 3, or 5. So the first thing I recognize is that 10 is actually 2 times 5. So I can rewrite this as log base a of the square root of 2 times 5 over 3. My next line would really convert this radical into an exponent. So log base a of 2 times 5 over 3 is actually raised to the power, this whole thing, 1/2. Then what I can do is I can write this 1/2 out in front of the logarithm. So we have 1/2 log base a of 2 times 5 over 3. And now at this point, I can apply my product and quotient rules to make this logarithm a few different logarithms. So we're going to get 1/2 times. So the 2 is in the numerator, so it's a positive log base a of 2. 5 is in the numerator, so that's positive as well, log base a of 5. Then we have this 3 that's in the denominator, minus log base a of 3. Then I can close my brackets. Now I have an expression that has all of these things up here. So we can rewrite this as 1/2 times log base a of 2 is 0.3562. And then log base a of 5 is 0.8271. And then we're subtracting log base a of 3, which is 0.5646. Then we can get out our calculators and do our calculation. So I get 0.3093.